Hey everybody, today we're going to look at Dalton's law of partial pressures. This is another of the various gas laws. It's a little bit different in the way it's handled, but it's pretty much the same idea. Okay, so anyway, let's take a look. What Dalton was doing is he was looking at various gases mixed together. So he was looking at adding gases together. So what I'm talking about here is, let's say you have a container and you have in here hydrogen gas. Well, he said, what happens if I added in oxygen gas? And what happens if I add in nitrogen gas? Well, what he found was that if you calculated the pressure of the hydrogen by itself, okay, you calculated the partial pressure. These are called partial pressures because if they're a mixture, we have oxygen and nitrogen in here. We have three different gases all in here. There's going to be a mixture, so we're talking about the partial pressure, the portion of the pressure that the hydrogen is contributing, and the partial pressure of the nitrogen. And he found that if you add all three of these together, you get the same total pressure that's inside our overall container. So the idea is that these individual gases don't really recognize the other gases. Nothing happens to the partial pressure of the hydrogen when I add the oxygen in there. The partial pressure of the hydrogen remains the same. The pressure of the nitrogen is the same thing. If I measured it out here and everything was the same volume, temperature, and number of moles of nitrogen, then the partial pressure of nitrogen would stay the same, and so would the other two gases. And that's the general idea of his experiment. Anyway, so if we have three gases all in the same container, well, the temperature of all three gases has to be the same because they're all in the same container. The volume, because we're looking at the size of the container as our volume, not the individual gases themselves, all three would have the same volume and temperature. So if we looked at the ideal gas law for pressure times volume nRT, and we divide both sides by volume, what we end up with is this equation here. So we can calculate the partial pressure of individual gases, this could be hydrogen, oxygen, or nitrogen, just by looking at the number of moles that we have there. So really what he's looking at is the pressure and mole contribution. Like what happens if I increase the moles, keeping volume and temperature constant? Well, my pressure goes up. And what I'm doing is I'm just adding more moles of gas by doing this. Doesn't matter what the gases are. So all gases in the same container at the same temperature, meaning that the volume is the same and the temperature is constant, you could simply add the moles of all your gases together, get a total number of moles, and if you want to find the total pressure in the container, just use this equation here and figure out the total number of moles. Now, I'm going to show you some examples with this. I know this is probably not making much sense just looking at the equations like this, but when I do an example problem, it'll make a lot more sense. All right, one very applicable portion or way we use Dalton's law is when we are collecting gases over water. And this is something you really want to watch for when gases are collected over water. All right, so let me show you what I'm talking about. Say we have a reaction over here, chemical reactions occurring. We have hydrochloric acid and we add zinc metal to it. Well, it's going to produce hydrogen gas. You should remember that from first semester. Well, if we have a container here of water and a jar filled completely to the top with water, and we bubble in that hydrogen gas, we can get those hydrogen gas molecules to be separated from the outside air molecules, right? If I just let this go off into the air, well, it's going to mix in with everything else. We're not going to be able to isolate the hydrogen gas. So this is a way of isolating gases by collecting them over water. Because as that gas is generated, it's going to push down the water and just have the hydrogen gas. So in here what I would have is hydrogen gas. Now, not only do I have hydrogen gas, but because of the fact that I have water here, water is going to go into the gas phase. You should know about humidity and the fact that water vapor exists. Well, you're going to have a gas mixture. So I don't only have hydrogen in here, but I have hydrogen and water. So this is a combination of gases. So that total pressure is not just the pressure of the hydrogen gas we're collecting, but the partial pressure of the hydrogen plus the water. So that total, if I measure the pressure in this container, it's the sum of both of those gases. Now over here is a table. And this table shows us what the partial pressure of water is at a particular temperature. Because you should think about this, right? If you heat up the water, more water particles go into the gas phase. So at higher temperatures, we would expect the partial pressure of water to go up. So temperature goes up, partial pressure goes up. All right, so that's essentially the idea.